It's a pleasure for me to come speak to you all tonight. There's a lot that needs to be said about this because unfortunately, as the legacy of Ted Kulongoski kind of died off, the idea of carbon cap and trade sure hasn't. And we have some real loonies, and I don't like to use names like that, but we have some loonies in Salem that really are trying to push this carbon cap and trade today. And as we've learned more and more about the science and what drives things, there's less and less reason to do it. What I'm going to present with you tonight, or present to you tonight, is not my work, but it's new work. The author of the work is Dr. Edwin Berry, and Edwin Berry is an atmospheric physicist with a PhD in that, and he's got an engineering degree from Caltech, and he's a certified consulting meteorologist, and he's done a lot of work with analytical systems and engineering. If there's anybody who understood how to look into the contradictions and conflict of how carbon goes in and out of the atmosphere, Ed would sure be the guy to do it. And I always figured that this is one aspect of climate that I never looked at. With all the things the IPCC has screwed up, I figured they could at least get carbon stuff right. And I never looked at it, so I didn't pay any attention to it, and every assumption I made about it till Ed came along was that we are adding the CO2 into the atmosphere and we're causing the increases. Ed's research shows that that's simply not true. And I was honored to be able to look into to his work as he developed it, because he's part of the global warming realist groups. That's how I got to know Ed. And he's actually published a paper on this now, which has been submitted to a scientific journal. He presented his first results in January to the National American Meteorological Society. So I talked about this with Ed. He's let me use some of his slides. I've developed some of my own, and I'll present this tonight. Before I do that, though, I wanted to ask you guys, did anybody see this in Sunday's Oregonian? I mean, this was disgusting. A full-page ad, and it says the time for climate action is now. What's disgusting about it is, if you want politicians signing it, that's one thing, but here's 70 people with PhDs, and a lot of them are from my alma mater. And I'm ashamed of this. There's no reason to put it in there. And one of these guys, by the name of Christopher Butenhoff, I'd had some conversation with back in 2014 because we were talking about the feasibility of carbon taxes back then. I exchanged emails with him, and using the old philosophy on carbon and how it builds in the atmosphere, we actually came to an agreement about the fact that the human contribution in the state of Oregon is very small. It's too small to have any significance to causing any change in the climate system whatsoever, even if you believed that CO2 was causing climate change. So we had that understanding, and then here he signs this thing. And the last paragraph says, the Clean Energy Jobs Bill, HB 2020, will overcome these challenges. It will reduce global warming pollution across the state. Oh, doesn't that sound good? Invest in clean energy, and it will protect our community from the impacts of climate change. Now, how could a PhD in physics sign this when just 5 years ago he admitted that such a bill would have no impact on the climate? The only answer I can come up with is there's money involved and it's politics. These people are basically doing a sales pitch for an energy tax. That's all HB 2020 is. And then we've got some of our own Republicans that have defected, and I don't understand why Greg Walden would be doing this, or Cliff Benz. I'm disappointed in them. Maybe they need to see this and take a look at some things. I certainly don't want them going crazy and jumping off to the other side, because there's a lot that they could understand that would help them realize this is a waste of time, and it's just going to steal money from people. Well, anyway, enough of that. I want to get into the presentation tonight because this is very instructive. And I'll start by presenting some logic of how people talk about climate change today. The logic of it is, if human CO2 changes the climate, now this is from an alarmist standpoint of view. If CO2 changes the climate, then bad things will happen. If it was changing the climate, of course bad things might happen. But then bad stuff happens. Could be a tornado, maybe a Columbus Day storm. Maybe we don't get the snowpack that we're supposed to get in a year's time. That's bad stuff. Therefore, human CO2 changes the climate. Do you see the illogical fallacy in this reasoning? This is how these people look at the world. It's silly. So events don't prove their cause. If Bill Gates owns Fort Knox, then Bill Gates is rich. That's a truism. If he had enough money to own all the gold in Fort Knox, he'd be rich. So if Bill Gates is rich, he therefore owns Fort Knox. That's completely illogical. Another example of how these people think when they're talking about climate change. A false accusation about an event and tying it to something that's not true. But they sell a lot of this stuff, and you know what? To an unwitting person that's not thinking carefully, that works. They've influenced a lot of people with this kind of logic. Well, so how is it that the IPCC got this carbon thing all screwed up? First, we got to get into the scientific method. It was Richard Feynman, one of the smartest minds in physics from Caltech, who said these things, post-Einstein. If you have a plausible theory, you make a prediction about what you think something should behave as, or what's causing it to change, what causes it to behave in a certain way. You develop your equations, and then you need some data to validate whether your theory works. If the data is wrong, the prediction is wrong, and the theory is wrong. There's no second going around saying, well, a part of it could be right. It doesn't matter who said this, how smart they were, what kind of degrees that they have. If they have a theory and they can't back it up with data, it's wrong. It means you scrap it. This is how science is supposed to work. Unfortunately, the IPCC doesn't look at things that way, and they become an increasingly political body over time. What do I mean by that? Well, first of all, let's take a look at some carbon budgets. And you know, before I looked into this, I didn't realize that, you know, there's a lot of carbon that goes in and out of the atmosphere. And I don't know if a lot of you are even familiar with that. When you read about what they do on the news, and they talk about so much human emissions per year, that it's 36 gigatons of CO2 that we put into the atmosphere by burning fossil fuels, that's a pretty accurate assessment. And it sounds like it's a big number. But then they take that and say, that is the only reason why CO2 is going up in the atmosphere. But look at the carbon budget. Let me see here. Is this the laser? Yes, it is. Look at the carbon budget. This is an older one. This graph, or this pictorial here, is probably about 10 years old. It said the total was about 800 gigatons of carbon in the atmosphere total, and it's actually closer to 900 today. I'll work those numbers up in a minute. But look at what's exchanged between the biosphere and the oceans. It's 200 gigatons. Every year, that's going in and back out, and we don't even see it. Now, there's nobody that disagrees with that assessment. This is pretty much accepted by carbon accounting. And then over here on the side, we've got fossil fuel emissions, 7 gigatons. We, compared to nature emits 2 orders of magnitude more CO2 and carbon into the atmosphere every year than humans do, combined. Now, that's something before I looked into the carbon problem that I even realized. Now, what the IPCC does is they say, okay, with this budget, we are certain that this cycle doesn't change and nothing changes it. It just stays static. And the problem with that is it's a direct contradiction to the ice core records and everything else we're able to measure about carbon. What we know about CO2 is that it's very sensitive to temperature, which I'll show you in just a few minutes. And it affects how much gets absorbed and how much stays into the atmosphere. So if the temperature is not staying constant, it's impossible for this budget every year to stay constant. Temperature would be changing it. So that's just a perspective. So what does the IPCC do with this budget? We'll start with our atmosphere, which today has closer to 900 gigatons of carbon in it. That's 900 billion tons. A gigaton is a billion. And then we have the oceans and the atmosphere. And their idea, which I'll show you in just a minute, is saying that this absorption and emission by nature is independent of temperature. They say temperature doesn't affect it, it stays constant. But the absorption depends on the partial pressure that's in the atmosphere. So the more of it you build up, it's like water in a pool. If you got a drain at the bottom, the pressure at the bottom keeps going up as you put more water in the pool. So the amount going out the bottom from the partial pressure will keep increasing. But their idea of how this works is they have 4 absorption drains, each with its own atmospheric proportion and rate of absorption. How can this be? How can nature's CO2 know that there are 4 drains, each one has its own absorption rate, and it goes out of the atmosphere according to the way the IPC formulates it? So we start with what they've done. We take the 900 gigatons, and this is their equation on the bottom. We take each one of these bins and we fill them to 100%. Now what's happening here is they take 900 gigatons and they assign that to bin 1. Bin 1 takes 15.2% of the 900, bin 2, 25.3% of 900, bin 3, 27.9 of 100, and bin 4, 31.9% of 100. And then look what they do. Then they have 3 residence times. The first one is 173 years. The second is 18.5, and the third is 1.19. So as carbon builds up in the atmosphere and it gets absorbed into the environment, if you look at this equation, this is level as a function of time. L0 is the initial amount of carbon assigned to A0, which is 15.2% of this number, and it doesn't decay by anything. The rest of the exponents here cause this rate to go down. So they're saying, in effect, that this bin will stay at 100% forever. So the drain's clogged, it doesn't work. How can that be? This is not physical, it's impossible. But this is what they do, this is how they formulate it, and they've given no rational explanation for this. So let's just run it forward 8 years. 8 years later, if you ran their equation, here's bin 2, and it will stay this way forever. It doesn't matter how long forward in time you go with it. It'll stay at 100%. Bin 2 will be 98% of 25.3% of this total. Bin 3, 81%. And bin 4, this is the only realistic one, because they use perturbations from volcanoes and stuff to determine that should be about, I think they said it was a little over a year. But it's 3.5, It's about 3.5% left after 8 years. But notice how slow everything goes out of the atmosphere the way they calculate things. Is that true? It's not true, because they don't have any temperature dependency in this whatsoever. It is simply wrong. So if we were going to make a model that could work, that could accurately describe how CO2 goes in and out of the system, we first have to realize that the CO2 is sensitive to temperature. Soil conditions, oceans, everything. As the temperature goes up, more CO2 stays in the atmosphere. This source is from a geophysicist, Hardy, who put a research paper out that Ed thinks highly of. On the left-hand side of the graph, we've got CO2 in parts per million, and on the right-hand side of the graph, we've got surface temperature conditions. Now notice here on the left, this is a mean Earth temperature of 10 Celsius. That's pretty cold, because the mean in modern day times is actually 15. So this is a glacial we're talking about here, where you had an ice age going. And back then, it's around 200 parts per million. But then look what happens as you start increasing the temperature. You get it back up to the median temperature that the radiation physics says we should be at between glacials. That's about, gosh, I keep hitting the wrong button here. That's about 15 degrees Celsius, and notice how it goes up exponentially. By the time we're from 1850 up to where we are now, we're right about where Hardy says we should be. We have about 410 parts per million in the atmosphere right now. That's an exponential growth, and it depends on the temperature. The warmer the temperature, the less can be absorbed into the ocean, and the more the land begins to emit CO2 as well, because biological things begin to happen, rotting wood, insects, all of this stuff. It adds to the CO2 that goes into the air. So those are some of the physical reasons why you would expect this, but that's the reality of it. Now, where is it in the IPCC stuff they have anything that, like this? They don't even talk about it because it's wrong. So if we were to try to model this the right way, we'd start with the same thing the IPCC did. We have our 900 gigatons in the atmosphere. So here's Ed Berry's idea of a model of how to treat this atmospheric CO2. We start with our 900 gigaton total. Then we take a look at the nature's inflow, which is 216 gigatons a year. And that is set by temperature perturbations like I just showed you. It has nothing to do with much anything else. And notice we've only got one drain size. You can compartmentalize that drain size, but you don't have 4 of them. The absorption has to have, and the oceans and biosphere have to have the same access to those CO2 molecules as any form of the carbon that can take place in the real atmosphere. So the drain size is set by the same temperature perturbations. Then we have, on the left side, the human component. We're putting in about 9.8 gigatons of carbon. But the human inflow is independent of temperature in the sense that we use more fossil fuel in the wintertime when it's cold, less in the summer, but the hemisphere's seasons are the opposite, so it kind of balances out. We don't really change over the course of a year how much as human beings we put into the system. It's pretty much that, and it does go up because developing countries are starting to burn more fossil fuels, but it's their use of those, not so much temperature, that determines how it's going to go up. So, the outflow from such a system depends on the sum of partial pressures, just like the IPCC's model says, of both the human and the natural component. So the more of this you put in the atmosphere, the drain's going to take more of it away. It's not a linear process. So how would you formulate something like this? I don't want to focus too much if you're not a math wizard, so don't worry about that. We're not going to have a math test at the end of this. I'm simply showing this from the standpoint that I'm also videoing this, and I want to make it available to scientists so that they can see how I'm concluding what I'm concluding. So Ed developed a simple expression. And the first part of it says dr dt equals inflow minus outflow. dr over dt is just a derivative. It means the rate of change of the level of carbon dioxide in the atmosphere per unit of time. And it's equal to inflow minus outflow, which makes sense when you think about it. If more is going into the system than is going out, the level R will go up. If more is going out than coming in, you have a negative number for dr dt, and the level is going down. If inflow equals outflow, we have what we call a balance level. Because now, if as much as going out is coming in, whatever that level is set out, it's not going to change. So, Ed lets outflow equal to R over dt, which is the level divided by TE, which is a residence time. That's how much it stays, that's how long it stays in the atmosphere, which you can determine by empirical measurements. And it's set by the level partial pressure. So then, you just substitute that for outflow, then the balance level occurs when, like we talked about, if the derivative is equal to 0, now we have inflow equals outflow on both sides of the equation. And then inflow, or the balance level, is set by inflow times the residence time. You substitute 5 into 3, that's the expression you get in 6. The rate of change is equal to minus the quantity R minus RB over the residence time. And the analytic solution of that is the integral of the variables. So we won't go into the math here, but at the bottom is the result of integrating that expression. And then we have a function of R, or level, as a function of time, and it's equal to RB plus this quantity here. And notice, like the IPCC, there is an exponent involved. It's from the natural base E, and T is the actual real time, and TE is the residence time. So you can plug any numbers into this, and you'll get a rate of change of the balance level in the atmosphere, or any changing level. And if the balance level is below what the level is, that quantity there next to the exponent becomes a negative number, and it decays to 0. They'll get a new balance level, and vice versa. It can be positive. It'll do the same thing. It just depends on which way it's going, whether it's up or down. So that's Ed's equation. Now, if you want to know how this is accurate, and you want to know Ed's not full of baloney, how would you do this? It turns out there's a way to do it, because nature gave us the data we need to validate Ed's expression. Do you guys remember back in the 50s and 60s when the USSR and the United States were blowing up hydrogen bombs, nuclear testing in the atmosphere? This was going on all the time, and it was putting a new form of carbon into the atmosphere that had 2 extra protons. It was a carbon-14 atom that still combines with 2 oxygens to give CO2, but it's a special type of CO2. One of the last nuclear tests that was done in that era was by the Soviets, and it was basically Nikita Khrushchev showing off, and he had his scientists build a 58 megaton thermonuclear bomb. Now, 58 megatons is equivalent to 58 million tons of TNT. Imagine that going off in your backyard. They blew this bomb up over the Arctic Ocean, and it immediately caused worldwide condemnation. And it led to the treaty between the US and the USSR. Khrushchev was basically saying, don't mess with us Soviets. We can build devastating bombs compared to you people in the US. We didn't want to waste our time with it because it weighed 7 tons, 14,000 pounds. They barely got the damn thing inside their Tu bombers. And the scientists that put it in there said, when you guys drop this by parachute over the Arctic Ocean, you'll be about 30 miles away when it goes off, and there's probably a 50% chance the shock wave will destroy the airplane. But, you know, being the good soldiers they are, they got to do what they're told. Turns out it did catch up to them. It damaged the airplane, but they didn't crash. But it brought worldwide condemnation, and it led to a nuclear pact treaty between us and them, and so all atmospheric testing stopped. So now this carbon-14 is hanging out there that was a result of these nuclear tests, and guess what? The chemists were able to track this. Here's the carbon-14 CO2 absorption after the nuclear test ended. This is the nuclear test ban treaty right here at the top. And it was measured, these are 2 measurements from Bermondsey, Austria, and then also from New Zealand. And notice here when the testing was going on, first of all on the left, here's the percentage of modern carbon. 100% is the normal level. And then so when they were testing, we drove the CO2 levels because of carbon-14 way up. They went to like 180%. And then on the downside, this is where it gets interesting for Ed. Because on the downside, he's got some half-lives here. These are not radioactive half-lives. They're half-lives of the carbon staying in the atmosphere. So what we're measuring here on the downside is the absorption of this particular isotope of carbon into the environment. And notice, it's not linear. It's exponential. That's what Ed's equation describes. And in fact, he took these points where they were able to measure them and determined the residence time for the 14 isotope was 14.4 years. Now it turns out that's not quite the case. It was actually a little longer than that, because these were before the adjustment times where they let the carbon-14 circulate all around the Earth and become equal pretty much everywhere. When they got it to that point, then the guys who do the radioisotopes, then they said that the time to start seeing how this deteriorates in the atmosphere is from 1970 forward. That's called their adjustment time. And the residence time is following that curve downward. But Ed's equation, each one of those dots on this, on the left-hand side, by the way, that's per mil of carbon, which is like 0.5, 0.4, 0.3. Per mil is per thousand. Then they multiply that fraction to get the appropriate amount of carbon. So that's what the left-hand side is. And the right-hand side, same thing. It's a time scale where we show the buildup of the 14 isotope and then its decay by being absorbed into the environment. Now it's getting absorbed because no more is going in. The testing stops. So what's there, we're just watching nature get rid of it. And each one of these points, Ed plotted these. That is a perfect match. Where have you seen that before in science, especially climate science? So Ed's equation works like a charm, and we use the information from nature to determine that. It's beautiful. It's a beautiful thing. Now here's how we know the IPCC is all messed up, because you can plot their things. Now this is, with Ed's equation, I use 14.4 years. That's when he drew this graph. That's before the adjustment time, which is now makes it 16.5. Doesn't matter though, the IPCC's equation stays the same. It didn't change. So you can compare it to the Byrne model, which is the IPCC. That's the red line. And if you see the Byrne model and how it takes care, takes care of this carbon, it crosses the true line of absorption. It's way too high. It doesn't work. It's way up here. The correct equation that Ed has beautifully takes it out of the environment, just like nature is absorbing it. And then using the IPCC's own numbers for carbon-12, which we have no reason to challenge yet, if you apply Ed's equation to those, the residence time for that is 4 years, and look how fast the fossil fuel burning goes out of the atmosphere. It's fast, very fast, and it isn't anything close to what the IPCC has misled us to believe that it is. That's amazing. If you can match a theory, an equation, with real data from nature, you've got something here. So this is why we're excited about this. At least I am. The IPCC is probably furious. They don't want you to see this. So what are the consequences of using the correct equation for the carbon cycle, which would be using Berry's equation? Well, recall that the balance level of atmospheric CO2 is that inflow time, RB is equal to inflow, multiplied by the residence time. So we'll use the IPCC number of 4 years. And let's see what result we get. Nature's portion of atmospheric CO2 in the balance is 98 parts per million per year. That's what nature emits in this continuous carbon cycle. At least they call it continuous. You multiply that by 4-year residence time, you get 392 parts per million. That's nature's portion of the total that's in the atmosphere. The human or anthropogenic portion is taking our emissions, which we've figured at 4.5 parts per million by volume per year, and we multiply that by the 4-year residence time, and we get 18 parts per million. So the natural component plus the anthropogenic is exactly equal to what's in the atmosphere today, 410 parts per million. What does this mean? The human component of atmospheric CO2 is only 4.4% of the total. Imagine that. And yet we're told it's 100%. Everything we're dumping in is what's causing it to go up. Baloney. It's not the way this works. So just for fun, I took those numbers and I plugged them into the University of Chicago's Modtran radiation code and just use the human component, the 18 parts, to see what temperature response it gives. And you get a little over 0.3 of a watt per square meter increase in radiative forcing on temperature just using that, if you believe it. But that's assuming that everything that's absorbed gets sent back to the surface, and the negative feedbacks we know happen in real science actually don't even prove that. I'm giving them the benefit of the doubt on this. So that's equivalent to 0.06 of a degree centigrade on temperature, which is, this result is undetectable and it's lost completely within the range of natural variability. We can't even see something like this. Now notice, just like in the graph I showed you, where it showed the exponential relationship of temperature to CO2, using Ed's equation, how does that work with that exponential growth we're talking about. So let's say that we get a temperature perturbation and the residence time is increased by 2 years because of it. So now the nature's component would be the 98 parts per million that's upset again by this temperature perturbation. And if we increase it to 6 years, now that level is going to be allowed to go up to 588 parts per million. The anthropogenic fraction, again, are 4.5, but now we have a temperature perturbation, so we can't absorb it as fast. And now our TE goes up to 6 years. The human fraction is 27 parts per million instead of the 18. So the sum would be 615. With just a 2-year change in the residence time from a temperature perturbation, atmospheric CO2 would continue to be allowed to go up unabated to 615 parts per million. That's a pretty significant increase. But we're not driving it. The fraction of human to natural emissions does not change from that 4.4% unless human emissions continue to increase to make their own new balance level. Nature is just absorbing too much of it. So no matter what you change the residence time to, the human fraction is going to stay at 4.4%, even though the individual number can be larger. Imagine that. Now, another thing the IPCC does to try to say that we know humans are driving atmospheric CO2 is they take a ratio of carbon 13 and 12. If you're burning fossil fuel, it's more associated with the carbon 12 isotope than the 13. The 13 is found more from nature that's kind of hanging out in the atmosphere. So they say if the ratio is changing and we burn more fossil fuel, increasing the 12 carbon, it's obvious because that's in the denominator, the ratio is going to fall. And it has fallen. They measured that, so they're saying this is proof that anybody who argues with us is wrong because the fraction is going down, and we know if it's doing that, it's because of humans burning fossil fuels. Well, got bad news for them on this front, too. This graph is from Dr. Murray Salby. Salby is an atmospheric physicist, actually in atmospheric science. He was from Colorado State. And he's done his own independent work on this. And we have satellites now that can measure these various different isotopes. And notice on the top here, this graph from Berry shows that the green line is temperature and the blue line is carbon-12. Notice how they kind of follow each other. Again, proving there's temperature sensitivity to how much hangs out in the atmosphere, whether it goes up and down. But on the bottom here is carbon-13. It's inversely proportional to temperature. So if you get a perturbation that causes 12 to go up, 13 is going to go down. So that ratio is not something you can use to say we know it's being caused by humans. Here's another measurement of the satellite data that shows there's an anti-correlation between carbon-12 or carbon-13 and temperature. As temperature goes up, carbon-14 and its isotope goes down. So this makes the decreasing ratio of 13 to 12 unreliable as proof human emissions drive atmospheric CO2. Now maybe these guys didn't know that before the satellite started measuring it, but they do now. So now what's their excuse? There isn't one. Here's another thing we've discovered that really pours cold water on the IPCC. The burning of fossil fuels tripled after the year 2002. China started burning a whole bunch of this stuff. And here's the linear line that represents what we were doing from 1990 to 2000. After 2002, this tripled. It went up. What happened to the atmospheric CO2 in the real atmosphere? What happened to it? Did it change as we tripled the amount of fossil fuel we were burning? No, it didn't. Yet the atmospheric CO2 increases remain constant. Now, they're not exponential like Hardy's work showed, but the reason for that is that temperatures haven't gone up very much at all since 1998. Besides the El Nino of 2015 and 16, the temperature's been steady. And Murray-Salby tells us what increases in the atmosphere is actually an integral of the temperature, summing it all up as it goes up. But then if it levels off, it's not necessarily going to drop, but it's not going to go up as fast. It'll start leveling off. That's what this line here shows. And the little red dots, or the little red squiggles here, are what Murray-Salby calls the CO2 cha-cha. 5 steps up, 4 steps down. 5 steps up, 4 steps down. When you have this sort of relationship, you get a buildup because you're putting, more is not getting absorbed than is coming out by the natural cycle, which is plotted here. So if you're not seeing a change in global atmospheric CO2 after fossil fuel burning tripled, this would be impossible if we were causing the increases. These people do not know what happened to the extra CO2 that we burned. The record is not changing. Humans do not control atmospheric CO2 or the climate. I think that this overview of Dr. Ed Berry's work proves this. I'm just absolutely fascinated by this because I'm only interested in one aspect of presenting any of this stuff, and that's in the search for truth. What the science shows us today disagrees completely with the IPCC and these politicians. I don't want to leave tonight before getting an opportunity to dump all over climate models. I just love doing that. And I want to show you how poorly these things perform compared to looking at somebody like Ed Berry's work, which is a perfect match to the data. So here's performance of climate models. The green line is a climate model developed by James Hansen, infamously known for his promotion of climate hysteria. And this model here with the green line is called today an RCP 8.5, meaning no change in business as usual. Humans just keep emitting the same CO2 that they do on a yearly basis, and there may even be some buildup in it from that. And so look where they got the temperature today based upon business as usual, and that's where we're at. We haven't done much of anything here. We're still putting a lot into the atmosphere. It's been growing. It's 36 gigatons now. In a year or two, it may go up to 40 with the developing worlds coming up. So we're not cutting back on it at all, but look what the temperature prediction was. 1.5 degrees above the 30-year mean. Now, the purple line is the Hadcrut temperatures, the actual measurements. And the yellow one is scenario B from Hansen, which means we cut some emissions. And scenario C are drastic cuts in emissions going back to 2002 levels. We're not qualified to have these two models. I mean, they don't qualify to be in the end result. You can't use these because that's not what's happened. We've continued to burn CO2. So the only fair comparison is looking at the green graph that shows he's got us way up here, and the purple line shows we're nowhere close. We're about 0.4 above the 30-year mean. And this was during a period where we changed ocean phases to warm phase PDO, and you can expect natural warming. That's all this shows. And it also shows what a miserable failure climate models are. So like Feynman said, if your data doesn't match your prediction, it's wrong. And it doesn't matter whether you got 30% of it right or 20% of it right, it's wrong. That's how you grade physics and any theory that's associated with it. So to conclude, the global warming debate is over. The issue is man-made, the data is man-made, and the crisis is entirely man-made. And so is the consensus. But it isn't scientific. Thanks for listening.